Last day, most probably we have discussed on spectroscopy. Am I right?
Yes, sir.
Hello. Okay. So spectroscopy, that one. Up to UV, I have already discussed, na?
Yes, sir.
Yes. Today we have to discuss on Woodward-Fisher rule, empirical rule. Am I right? Last day we have discussed up to this advantage and disadvantage of UV visible spectroscopy. Now we can start. All have joined. Now you are waiting for your classmates. Okay. We have to wait for 2 minutes again. Only you are 35. Do you have any question? What I have discussed in last week on spectroscopy. If you have any question, then you can ask me. Hello. Don't have question?
No, sir.
I don't have. Okay. Now we can start. Hello. Hello.
Yes, sir.
Okay. So today we will just discuss on the last topic of your invisible spectroscopy, that is the Woodward and Fisher empirical rule for calculation of lambda max. Already I told you that lambda max is the specific actually spectroscopic observation of a particular compound, and that is the actually lambda max is very important at a particular position and at a particular concentration they are observance. So that is already I told you that it is a signature of the compound, means actually we can identify quite that this this spectrum for a particular pure compound, this one, and their lambda max is the identification mark. Identification marks means identification of the lambda max position. And lambda max we actually determine from experimental spectroscopic analysis. Spectroscopic analysis. If you have to take any spectrum of a compound, then you have to make the solution of the compound, and that have to measure at a very low concentration, and you will get a spectrum. And there are different peaks you will observe, and they are sharp peak. That one actually might be 1, 2, 3 or like this. So their lambda max position is very important. And this lambda max position that we can calculate as we calculate by experimental method. And similarly, Woodward and Fisher also give an empirical rule. Empirical rule means actually it is not exactly, but it is very close to the experimental one. And that rule is applicable for some compounds, and that we will show you in the next slide. But before going details about the Woodward-Fisher rule, I will say you. You see this the different structures. Different structures. This is the annular. Both are the annular, but this is the homoannular. Homoannular means মোশান একটু পরে এসো আমি ক্লাস নিচ্ছি Homoannular means the double bond in the same ring. You see here, these double bonds are in the same ring, but in this case, the double bonds are in different ring. That is the heteroannular annular compound. And these double bond, both the double bonds are exocyclic with respect to this ring structure. Here only one exocyclic double bond. This double bond is known as exocyclic with respect to this bond. Okay, so that is very important. And another important structural features, that is the cis and trans. Cis and trans, this is the trans word, means actually this moiety of this ethylenic double bond as well as this one, they are in trans position. They are in trans position, this double bond and this double bond. And here also the trans word, that is the double bond is in trans position. Okay, this is the in trans position. So this is very important to measure the empirical one. Now I will say you the parent compound. Parent compound means the actually ring structure. If it is the homoannular, then lambda max, they are basic. Basic means that is the that will be the 253. If it is the heteroannular, if it is the heteroannular, then it will be 214. 214. And apart from this structural lambda max value, different substituent, different double bond, different position, different other functional group that actually have to your total value, and ultimately we will get a summation of the lambda max, and that will be close to the experimental one. So different cases, how much amount of lambda max will be added, that is actually explained here. Double bond extended conjugation. So any double bond is added as a conjugation, then in each case 30 nanometer have to add. 30 nanometer have to add. If any alkyl substituent or ring residue is there, then 5 nanometer you have to add. Exocyclic double bond. If within the compound one exocyclic double bond is there, then in addition your total 5 have to added more. 5 have to added more. Similarly, polar functional groups, suppose ester, alkoxy, chlorine, bromine, or amine. If it is the secondary amine, means if it is attached with the carbon, then it is the tertiary amine, then again that have to add 60. So these are the increments. So increment and basic, I think these terms are more familiar in the pay structure. Actually, in different government employee, their pay structure that is formulated in such a way, there is a basic, then have the DA, house rent, transport allowance, so different hazard allowance, car allowance. Okay, so that is the extra. So similar, same thing is here. That is the basic value. That is the for the homoannular or heteroannular, 250 and 214. Then these are the increment for different substituent. Okay, so this is the common actually assumption means actually based on this value we will calculate the next one. Now you see here these two structures are given here. This is the heteroannular, this is also the heteroannular, and with respect to this heteroannular you see here, so as it is the heteroannular, so their basic value 214. And these are the three substituent. This actually bold actually CH2 bond. This is the another bond. This is another. So 3 into 5, 15 have to add it. And this double bond is exocyclic. That is that have to add extra more 5. So if you add these three part, then we will get 234. But if you measure the lambda max of a compound in a experimentally in your visible spectrophotometer, then you will get it 234. So only one difference, only 1 nanometer difference we get your experimental and your calculated one. Calculated means based on the empirical formula of Woodward-Fisher rule. The next one you see here it is also the same thing, the transoid heteroannular ring system, that 214 nanometer is the basic one, and 3 ring residue are there. You see here one bold line means actually this double bond attached to the CH2 ring residue. This is also the ring residue. This one is also the ring residue. So 3 into 5, that is 14, 15, and one exocyclic here also there, and here another ethoxy group is there, ethoxy. So for ethoxy 6 nanometer you have to add more. So that will be 240. If you add this one, 240, and observed value is the 241. So it is also the very close. So Woodward-Fisher rule as well as your experimental value, that is very, very close, and that is accepted for empirical calculation. What I explained, is it clear to all of you? Hello? I have to explain or something. Hello?
Sir, please.
Sir,
Sir,
exocyclic
the
double
ring
bond,
residue
please.
part.
Exocyclic double bond, yes. Exocyclic means one double bond that is with respect to this ring system. This is the exocyclic, means that double bond actually attached to this ring. Okay, that is known as exocyclic. This is the cyclic system. This is the exo. Okay, here also the exo. This one is the exo. Here two are exo with respect to this ring. Okay, two are the exo with respect to this ring. Means any double bond attached to any ring. So this double bond attached to this ring. This double bond is attached to this ring. Here this double bond is also attached to this ring. But this double bond is not attached to any other. Okay, directly. So that is the exocyclic. Is it clear? Hello?
Sir, the ring residue part, sir.
Now, bolo.
Sir, I couldn't understand ring residue 3 into 5, how it is coming.
Yes, yes. 3 into 5 years. You see here, this is the conjugated system. This is the conjugated system, and actually homoannular or heteroannular that have to cis or transoid means that is the conjugated system. So this double bond system attached through this CH2 unit. Actually, this is the ring. Actually, this one is known as ring residue. That means the part of the ring. This is the another attachment with the ring. This is the another attachment. So 3 attachments are here. Here also the same thing. 1, 1, 1. Okay. But next example you see here. Oh, we don't have any other example. So if you follow any book, particularly William Kemp, J. Dyer, organic spectroscopy book, there are a lot of examples are there. You follow that one. Okay. You follow that one. Is it clear? Okay.
Yes,
if
sir.
you don't, okay. So next we will discuss on the infrared spectroscopy. What is infrared spectroscopy? That is also the spectroscopy, the instrument which measures the light absorbed or actually percentage of transmission of a particular compound when irradiate with a definite wavelength region. Okay, so infrared that is associated with the covalent bond or coordinate bonds. Associated with the covalent bond or coordinate bonds. So within the compound, we know the covalent bonds are overlapping of 2 orbitals with 1 electron sharing from each, or lone pair from one orbital to another vacant orbital. Okay, so that is our idea about the covalent bond or coordinate bond. Now, in terms of spectroscopy, we consider the bond. Actually, 2 atoms are attached through a spring, suppose. So that spring, actually each and every bonds within a particular environment, that always it actually vibrate. It always, the bonds are vibrate in such a. And if you supply energy, then this bond vibrate more. If you supply more in such a way, that will vibrate more. When it will be exceed the bond breaking energy, bond dissociation energy, then the 2 bonds, then the bonds will break. It might be the homolytic or heterolytic. Okay, so this is considered as a bond, as a spring in between 2 atoms. So that will actually vibrate. Okay, that will vibrate. So that is the infrared spectroscopy. That is the infrared spectroscopy. So IR spectroscopy provides a simple and rapid instrumental technique that can give evidence of presence of different functional groups, different types of bonds within the compound. Okay. Secondly, spectroscopy forms the spectroscopy dependent on interaction of molecules or atoms within the electromagnetic radiation. Actually, or it is the electromagnetic interaction with the electromagnetic radiation within the range of 1.5 to 15 kilocalorie per mole. So this amount of energy, if we express in terms of lambda, means wavelength, that is quite difficult to remember, but it is more appropriate or more easier to remember if we express this lambda in terms of 1 by lambda, that is the nu bar. That means centimeter inverse, and this is more appropriate as well as easier to remember, and this is actually we can measure from 400 centimeter inverse to 4000 centimeter inverse. So infrared spectroscopy, in x-axis the wave number that is plotted, and y-axis that is the amount of energy absorbed or transmission. So that gives a specific spectrum, means peaks, and that peaks are very specific for a particular type of bonds. Suppose carbon hydrogen, carbon nitrogen, carbon carbon bond, carbon oxygen double bond, carbon oxygen single bond, or different types. What type of bonds we observe in organic compound? Each and every bonds is specific, and their wavelength is also specific, and that we can actually observe in infrared spectroscopy. And from there we can say what type of bonds are there within the compound that we can assess. Okay, we can assess. So infrared radiation refers broad to the part of the electromagnetic radiation already I have discussed between the visible and microwave region. So that is corresponding to the 4000 to 400 centimeter inverse. So repeatedly I told you this is the actually energy correspond to radiation that we apply into the compound. And what I told you, that is not required to repeat. Actually infrared radiation that is associated with the 1 to 15 kilocalorie per mole, that is equivalent to 400 to 4000 centimeter inverse. And within this range, actually rotational as well as vibrational modes we can actually irradiate and as well as excited. Okay, and that is that amount of energy when absorbed by the molecule, that will actually reflect in our spectrum. Spectra is a plural and spectrum is a singular number. Okay, so since the functional group of organic compounds includes specific type of bonds, always remember within the compound, carbon hydrogen bond, carbon nitrogen bond, or carbon carbon, that they are stretching frequency, that means at which wave number that will absorb energy, that is compound to compound that differ, but that have a particular range, so that is very, very important. So this is the characteristics of the compound as well as the characteristics of the particular bonds, and these variation are quantized and they occur when the compound absorb IR energy in particular region of the portion of the spectrum. Okay, next, actually this is the potential energy diagram. That is actually plotted against the intermolecular distance. So when a bond vibrate, and vibration, their frequency, they have a frequency, and that have a different V equals to 0, 1, 2, 3. This is very, very specific and quantized. So vibration at the low energy, if you supply low energy, that will vibrate comparatively in slower. Okay, that will be the nu will be the less. When it will be, if you supply more energy, then their bond distance will be more and potential energy will be more. Okay, so this curve you see are when the distance when amount of energy is supply more, potential energy of the bond vibration that will increase. That will increase, and that depends on the distance of the two atom. Distance of the two atom. Rotational is vibrational levels associated with some rotational translation. Rotational translation. Rotation already I told you. If you supply certain amount of energy initially, that will first the molecule translate, second that rotate, third vibrate, the fourth one is the electronic transition. Okay, so in this case each and every vibration levels that associate with the rotation levels. So these are the very also quantized but very minute, very discrete level, but these are quite actually broad range of vibration. Okay, so these are the mode of vibration with variation of potential energy, and as well as their distance, how it varies with the amount of energy supply. Is it clear? So infrared radiation is the is within the range suman 12,800 to 10 centimeter. But throughout this range, if you try to take, then it is very clumsy, and it will be very tedious to identify. But we consider only 400 to 4,000 centimeter inverse. From there we get a different information which are important for our analysis. So if we
Sir,
consider from the hello.
yes, sir.
Do you have any question?
Yes, yes, sir. One question.
Bolo.
Sir, for the Woodward rule, do we need to memorize all the cases for alkylated substitute, for exocyclic?
Today, let me to say, actually today just one class I have taken. This is the second day, and today I will complete. Okay, so within two class, it is very difficult to capture the total subject. And this is the actually spectroscopy, the subject particularly deals the chemistry people not only, but more important have to deal by the chemistry peoples. And throughout the tenure of the academic tenure, from BSc, MSc, PhD, even we are professor, and also at the verge of our service life, we are also learning, we are also doing some work. Okay, so it is the endless subject. Okay, each and everything is not required to remember, but you have to idea. You have to keep your idea proper. Okay. So these are the general statement. Already I told you. Yes, one thing you see here. The general vibration frequency of a particular bond depends upon the relative stiffness. Stiffness. What is the stiffness? Actually, stiffness is the strongly bound. How much is strongly bound? Okay. Carbon-carbon single bond, that is loosely bound. Carbon-carbon double bond comparatively more than single bond. Carbon-carbon triple bond comparatively more than double bond. So bond multiplicity is inversely proportional to amount of energy required for breaking. So single bond, if you have to break, less amount of energy required. If double bond, comparatively less, more than single bond. If triple bond, then more than single bond. So their vibrational frequency also changes. So triple bond are steeper. Okay, triple bond are steeper and vibrate at higher frequency. Vibrate at higher frequency. So bonds are more steep that vibrate at higher frequency. Okay, and double bond comparatively less than the triple bond, and single bond less than the double bond. Okay, so stiffness is the directly related to the K value as per Hooke's law. As per Hooke's law, I will say you about the Hooke's law. So I will explain that one. So again, that is related to reduced mass. Actually, the atom which are attached within the compound within the bond, so their reduced mass is indirectly inversely proportional. Inversely proportional. So mass of the bonded atoms, light atom vibrate at a higher frequency, heavier than the heavier atoms. As well as it depends on the geometry. cis or trans or other steric factors also govern the frequency. Now I will say you about the different type of bond bending and stretching. Bending and stretching. These are the two different terms. So already I told you that bond is actually attached to atoms or two balls through a spring. So that spring, if we consider as a spring at the bond, it is not a spring actually. It is quite easier to actually realize. Okay, so the bond that can actually stretch. Stretch means actually it will vibrate. My camera is on. Are you visible? Am I visible? Hello?
No.
Hello?
No, sir.
Okay, so
No, sir,
bonds
you
are
are not visible.
if these are stretched in symmetrical way, that means at a same time it will stretch outwards and inwards, in such a way. Okay, this is the stretching. This is the stretching and symmetrical stretching. But asymmetric stretching, one is outside at the same time, one is inside. Okay, so one is inside, another outside, like this. Okay, so in such a way, so that is the actually asymmetric stretching. So stretching means actually this is the stretching. Okay, this is the stretching. And bending or rocking, actually bending is the bonds actually not stretch but that will bend. Actually this is the bending. Actually you just watch me. Actually the hands, if we hang in such a way, so this is the bending. So this bending, either if it is come in the same way towards center, then it is the scissoring, and if this is the rocking. Okay, this is the rocking. One is the front, another is the back. One is the front, another is back. Or it might be at a time it will be both in same or and back, or one is front, another back. So these are the different mode of bending. For bending purpose, energy absorbed less. Energy required comparatively less. But stretching, it is more. So next you see here the different types of this video. What do you mean by symmetric, asymmetric, plane of scissoring, and different types of bending? What happened within the compound? For a different bonds. Okay, so symmetrically you see at simultaneously both the atoms actually go away from the carbon. Here one is coming, another is outing from the carbon. Here this is the bending, scissoring of bending. This is the in plane rocking. This is the out plane rocking. Actually out plane rocking means out always here planes are always changing, but here the planes are same, but here they are rocking. So out of plane, this is also the out of plane. The same thing is happening. Okay, is it clear? Now, have any question? Follow. Don't have. Hello. Hello.
Yes, sir.
Okay.
No question.
Okay. So essential requirements. Actually the fundamental characteristics for infrared spectrum, to provide infrared spectrum of a compound, that is the dipole moment change due to vibration or due to bending or due to stretching within the compound. Dipole moment, if it changed, then it will be IR active. Carbon dioxide actually due to their asymmetric stretching, that is that become what I say, that is IR active. Okay, so when we measure the infrared IR spectrum, then always we get a peak for carbon dioxide. Actually, when we put the sample within the instrument, then we inhale or we actually escape the our carbon dioxide, and that is actually sensed by the instrument. Okay. So greater the dipole moment change, more intense will be the absorbance. So their absorbance peak will be more intense. Some peaks are very sharp, some is very weak, and some is very faint, like that. And more smooth will be the vibration. The first one, the vibration occur within the absorption of IR energy. The dipole moment of the molecule must change during the vibration, but it is not necessary for the molecule to possess a permanent dipole. Thus, it may be concluded that absorbance of IR light depends upon the symmetry of the molecule. Depends on the symmetry of the molecule. So, depending on the symmetry, their spectrum will be specific. And more symmetrical compound, there don't have any IR active, suppose hydrogen, oxygen, or nitrogen. Okay, there is no any dipole moment change due to their vibration or bending. Actually, vibration within the vibration is possible, bending is not possible within the diatoms. So greater the symmetry, less will be the absorbance of the IR energy, and consequently less will be the vibrational translation. So this is the main features of compounds that will actually sense IR or not. So symmetric molecules like hydrogen, oxygen will have less vibrational changing, whereas the CO will have greater vibrational transition. Similarly, carbonyl group, CO group, will be a greater probability of vibrational transition, because due to carbon-oxygen bond stretching, their dipole moment change more than the other cases. Similarly, ethylenic double bond also the same. Again, in case of cis isomer, vibrational transition will be more, because they try to avoid the actually steric repulsion. When it avoid, then it actually distorted from its planarity, and double bond that is partially become distorted from the double bond character, that is single bond plus certain percentage of pi bond. So that actually changes. So due to this structural features, IR spectrum that varies. Now you see here, this is the spectrum of a very simple compound, that is the benzene. I think all you know, benzene is colorless liquid which is used as a solvent in laboratory. And this benzene, within the benzene, how many types of bonds are there? Number one, that is the 6 number of carbon hydrogen bond. You can count 6 number of carbon hydrogen bond, and 3 numbers of carbon-carbon single bond, and 3 numbers of carbon-carbon double bond. So, but it is not exactly single bond, exactly double bond. Do you follow me? Not exactly double bond or single bond. So that is due to resonance, which one you are observing as a single bond, next moment it will be the double bond. So carbon ethylene carbon-carbon double bond, that is close to 1.32 angstrom. Am I right? Carbon-carbon double bond, ethylenic double bond 1.32 angstrom. But carbon-carbon single bond 1.52 by 1.54 angstrom. So what is the expected of bond length? If we measure the bond length of the carbon-carbon single bond and double bond, or if you try to measure the carbon-carbon bond distance in benzene, we will not get two types of bond. We will get only single type of bonds. So that is their bond length. What is the expected bond length of benzene, carbon-carbon bond length in benzene? Anyone can say?
Sir, between carbon-carbon single bond and carbon-carbon double bond.
Okay, but what is the wavelength?
So
What will be
38.
the observed value? Anyone? You have done so many multiple choice question for JEE main advance. Huh? Hello. 1.39 angstrom. Always remember 1.39. It is in between double bond. It is more than double bond, less than single bond. Okay. So due to resonance. So here that will be the same case. The carbon, this carbon will be for a particular moment it is the sp2, another moment it will be the sp3. If it is change the double bond or single bond character, so their hybridization also be changed. Sometime it will be the sp2 and sometime it will be the sp3. So sp2 carbons attached hydrogen, their stretching frequency that appear 3060 centimeter inverse. This peak that is very important for sp2 carbons H bond. But another moment it will be sp3. So that is 2960. Okay. So two types of bonds are there. That is the carbon-carbon single bond and carbon-carbon double bond that we can say from this spectrum. At the same time, carbon-carbon double bond, that is 1600 to 1500 in between that peak as observed, as well as a carbon-carbon single bond, means actually it is not a for single bond, actually in between single bond and double bond. So their corresponding peak is very important for benzenoid structure, this benzenoid structure. So their specific wave number, that is very important to identify the compound, So in your literature, when any infrared spectrophotometer are purchased, so company give some data bank where the some common compounds, their spectrum already recorded, that have in their memory, and that actually compare, and that will give what type of compound is there. And you see here, this spectrum is taken from 4000 to 400. Actually 400 is there. So here two zones is actually, it is divided into two zones. One is the low frequency, that is the below 1400 or 1200. Means this zone from 1200 means consider, if you here, this is the 10,000, this is the 12, this is the 12. So this zone from 800, from 400 to 1200, that is the fingerprint region. And within the fingerprint region, generally the bending frequency that appear, bending for bending peak that actually appear. And above 1200, the stretching frequency for different bonds, particularly CH bond, NH bond, carbon-carbon single bond, carbon-carbon double bond, nitrogen-hydrogen bond, nitrogen-carbon bond, carbon-oxygen bond, different types of bonds. Okay, what we have in organic compounds that actually appear and gives a specific wavelength. So this is, you see here, this is the intensity, though it is written, but it is if you follow a standard book, that is there it is actually transmission or absorbance that actually written. Actually 100 minus absorbance, that is the transmission. Okay, so this is the transmission or absorbance or intensity versus wave number in terms of centimeter inverse are written here. Okay.
Sir, one question I ask, sir.
Hello.
Yes, sir. Sir, why the energy of carbon-carbon single bond, the absorbed mu bar is between 1500 and 1600, and that of CH bond is
Okay. So if
3500?
you follow a spectroscopic book, they are carbon-carbon single bond, carbon-carbon double bond, or carbon-carbon triple bond, or carbon-nitrogen bond. Each and every bonds, their particular range is given there, but not a definite, because not a specific for a particular compound. If you take the spectrum, then you will get a exact its wave number. Okay, wave number. Do you follow me?
Yes, sir. Sir, but my question was that why carbon-carbon double bond has lower wave number as compared to CH bond, sp2 and sp3. Sir, that is 3000, around 3000, and it is around 1500 to 1600. Is there any reason for that, sir?
This is the yes, carbon-carbon double bond. Okay, carbon-carbon double bond. So they are stretching frequency. Okay. that correspond energy that will absorb and remaining will be the reflected. So their corresponding energy is 15 to 1600. Actually, this is the range. 50, you see here, this is actually not clearly observed. It is the 1600, na? 15
Yes,
to 1600.
1600.
Now, bolo. This is the 1500. Actually, 1500 for benzenoid system, aromatic ring system. This one, and 16 it is the carbon-carbon double bond. But it is not exactly carbon-carbon double bond. It is partially single bond. Sorry, not partially single bond. I will say it is the actually partial bond. Is it clear?
Yes,
Hello?
sir. Yes,
Okay.
sir.
Okay.
Sir, but my question was not that, sir. My question was like why it is lower as compared to wave number of CH bond. Like it has higher wave number, na? Like
Yes,
around
yes, yes,
3000.
yes, yes. That I will give you the answer later on. Means actually, as per Hooke's rule, Hooke's rule, actually, we can predict that one. Okay, that we will predict. So many more bonds than the UV visible spectrophotometer fluorescence. The bands are also much sharper here because it is very, very specific that actually for a particular bonds that absorb. That is why it is very, very sharp one, and pattern is distinct for a given molecule except optical isomers. Okay, so that is very, very distinct. It is very, very specific for a particular compound, and good quality of tools means actually instrument that gives you a more authentic data. More authentic data. So all these things are written here, and these are the three spectrum. It is not properly visible. Actually, cyclohexanol, cyclohexanone, and cyclohexane, how their spectrum are changing, that is shown here. Actually, if you enlarge this one, it is not possible in my laptop in this position. So that you will see for a particular compound, cyclohexane, cyclohexanol, and cyclohexanone. They are different compounds. They are actually carbon-carbon single bond, carbon-oxygen double bond, carbon-oxygen single bond, or carbon bond. How they differ, but their basic value are almost very close. Almost very close. Okay. Now Hooke's law. Hooke's law, it is not new to all of you. Actually, already you have learned in 11, 12 in physics. Okay, in applied mechanics, you have solved so many questions. So Hooke's law, it is very, very applicable to determine the frequency of IR frequency. IR frequency. And IR frequency that actually formulated in such a way, nu is the vibrational frequency. Vibrational frequency equals to 1 by 2 pi root over of k by mu, not m. Actually, it is wrongly typed. That is mu. Okay. So what is nu? Nu is the vibrational frequency. That is in terms of centimeter inverse. Already I told you. And pi is the radial constant. K is the force constant. Force constant, and its unit is dyne per centimeter or gram per second square. Gram per second square. So gram per second square. And mu is the reduced mass. Mu, m, it is not m, actually it will be the mu. Mu is the reduced mass, that is the m1, m2 divided by m1 plus m2. Now you can say why carbon-carbon double bond appear in 1600, whereas your carbon-hydrogen appear in 2019, 2900 something, okay, or 3000 something, okay. So that is the reduced mass. It is related with the reduced mass. So higher the reduced mass, lower will be the frequency, and higher will be the frequency, lower will be the reduced mass. So if you calculate the reduced mass of hydrogen, carbon, and carbon, then you can easily determine your frequency when K value is given here. K value is 3 into 10 to the power 2 to 8 into 10 to the power 2 Newton per meter. Okay, this is for single bond. This is for double bond and triple bond. Double bond and triple bond. Okay, so for double bond into 2, for single bond it is 8. Triple bond into 3. Okay, so vibrational occur in order single bond less than double bond. Double bond is less than the triple bond. Now is it clear? But you ask me why sir CH bond appear at higher frequency, while is the carbon double bond at lower? That is as per this formula. Frequency is inversely proportional to the reduced mass. So if you calculate the reduced mass of carbon-carbon bond as well as carbon-hydrogen, then you will get your answer. So that will be
Yes.
the question. Okay, that will be the question for your exam. Do you follow me? Okay.
Yes, sir.
So for a stronger bond, K value will be larger, no doubt. Stronger means that triple bond is more strong than the double bond. Double bond more than single bond. So their corresponding mu will be the mu increase. As example of this, in order to increase the bond strength compared to single bond, double bond or triple bond, you see here carbon-carbon single bond that appear 10,000 centimeter inverse. So within the fingerprint region, So backbone carbon-carbon single bond, we generally not interested within the compound. Okay, whereas your carbon-carbon double bond that is the 1600 centimeter inverse and triple bond that is the 2200 centimeter inverse. Okay, so as the bond multiplicity increases, frequency increases. Now you see here carbon hydrogen. So carbon hydrogen, if it is the sp2, it might be sp3 like this. This is the sp3 carbon, then it will be 2900. If it is the sp2, then 3100. If it is the sp3, then 3300. Okay, so depending on the hybridization actually stretching frequency that actually changes. That change for heavier atoms. So you see here carbon hydrogen if it is there. So if you calculate their reduced mass, that will be correspond to 3000. If it is the carbon 1000, carbon chlorine 8000, carbon bromine 550 centimeter inverse, carbon iodine 500. So as the molecular atomic weight increases, actually their corresponding reduced mass increases. So their corresponding frequency decreases. Okay, so you can predict the position of different compounds if different bonds within the compound in your spectrum, expected spectrum. So this is the question. Calculate the absorbance frequency for CH stretching with a bond force constant K equals to 5 into 10 to the power 2 Newton per meter. So this is a very specific problem for your exam. That is your homework. Okay, is it clear? Hello, hello. क्यों किसी बोले ना?
Yes, sir.
Okay.
It is
Only
clear.
one student is responding, but other 95 or 96 students, they are silent. Huh? Okay. Now application of IR. So already I told you spectroscopy that have a versatile uses in our not only in our chemistry world, but in medical science, in metallurgy, in physics, even all the branch of science and technology everywhere. I in fact cannot characterize any compound. So qualitative and quantitative. Okay. So whether a reaction that actually proceeds or not, if you mix it to compound after a certain interval, if you have to change whether it is changing or not, then you can judge it by means of infrared spectroscopy. So that spectra will change from your reactant to products. Okay. So these are the different actually not only that, actually for organic compound, different drugs, molecule, different polymers, different actually nowadays which is very commonly used, the smart materials. Smart materials, not only the what we say benzoic acid, nitrobenzene like this. So all materials that includes that we can characterize by means of infrared spectroscopy. Okay. And now you see at the frequency ranges, different bonds they are expected. It is not exactly. Actually, compound to compound NH bond stretching will vary, but that will appear at a particular region, which that will appear near about 300, 3,400 around. NH that will appear near about 3,200 to 3,100. Similarly, CH that is close to 3,000, and carbon hydrogen that is close to sp2 sp3. Already I told you that actually they differ quite. Similarly, carbon nitrogen, nitrogen carbon oxygen, carbon oxygen double bond. So these are the different types of bond: carbon nitrogen double bond, carbon carbon double bond, carbon oxygen double bond. So all type of bonds where it will appear in the spectrum, that is shown here. And you see here, this is the what I told you, that is bending zone. Sorry, actually fingerprint zone, that is the for bending stretching that actually appear. So that is shown by this green line. So after 1500 or 1400, it is not so important, but in some cases we have to take the help. Okay. So this is the different compound, their stretching range. This is a chart of different compounds, their ranges, which will appear what will be the intensity. Okay. So when carbon-carbon double bond attached CH bond, that will 3010 to 3095. That will be medium. And their bending will appear 675 to 995. That will be the strong. Alkaline, alkyne means actually carbon-carbon triple bond attached CH, that will be 3300. That will be strong. So these are the different ranges of different types of bond that appear within the compound if you analyze. And all these data that have in the spectroscopy hard disk memory of the compound. And next, that is the fingerprint region. Already told you that is the 1200 to 700 centimeter inverse. 1200 to 700, that is the fingerprint region. That is actually here for bending, for different bending mode. You see here, this is the bending mode. Generally 400, close to 400, some metal halogen bonds that appear particularly, but 700 to 1200, that is for carbon-carbon bond system. Carbon-carbon bond system. দাঁড়াও আমি ক্লাসটা শেষ করি, 2-4 মিনিট লাগবে। And this is the actually zones specifically shown here. Actually, you see here the carbon oxygen, already told you, nitrogen, carbon, nitrogen, hydrogen, carbon, carbon, that appear near about above 3000 and within this field. And this is the carbon, carbon triple bond, carbon, nitrogen triple bond. This is this zone. This is the carbon, oxygen, carbon, nitrogen double bond, carbon, carbon double bond. This one. Okay. So you follow the spectroscopy, that is the William Kemp and J. Dyer organic spectroscopy. These are very authentic and authentic book. Okay, that generally students follow. This is the computer searching, means actually different. Already I told you different compound, very important compound, which are generally people handle, particularly in pharmaceuticals, in polymer chemistry, in dry drugs, insecticides, pesticides. Their data already have within the actually computer hard disks, means actually in their actually software. Now the quantitative analysis, actually quantitative analysis, though it is the complicated, but that we can done quite by means of infrared spectroscopy. What I told you, that already I have explained their applications. These are the different concentration with the variation of the concentration, different levels, carbon monoxide, methyl ethyl ketone, methyl alcohol, that can be identified by means of this quantitative analysis. This is the very common spectrum of carbon, nitrogen, and hydrogen containing compound. carbon, hydrogen, containing compounds mean what type of bonds might be there. If you draw the structure, different structure, then what will be the structure? Then you can actually get the hints from this spectrum. This is your homework. Okay, C3H5N. If you combine and draw different structure, you can draw structural isomer, and what will be the exact structure you will get from this spectra of the compound. And next one, this is the nitrile alkyne alkynyl group. This is the non-aromatic. This is the aliphatic hydrogen, carbon hydrogen. This is the one or more alkane group. Okay, so these are the different spectrum that is observed if you take such type of compound. So this is the end of the chapter. If you have any question, you ask me. Hello. Hello.
No, sir.
Do you have any
No, sir.
question?
No question. No, sir.
Don't have.
Sir, one thing, sir, there is so much data, sir.
Yes, yes,
What we
no
will
doubt.
remember for
Have
the
a
exam?
large number of data, but within 2 class, it is not uh, easy to actually memorize, but you have to practice this one. Okay.
So meaning what data we will learn for the exam, sir? I
You
want.
follow a book. You have to follow the book, and actually it is when it is required, then you have to follow the infrared spectroscopy for identification of your compound. For identification of your compound. Okay. अच्छा वीडियो ऑफ करते हैं. Don't have any question?